Hello everyone, welcome you back to the second session of Desh's. He'll be continuing with Pulsars, and like I introduced him to you last time, he's a very senior astrophysicist from Raman Research Institute, and he has done tremendously interesting work in radio astronomy. Over to Desh. Desh?
Yeah, thanks, Najam. Okay, I'm presuming that most of you who have managed to join today were there the previous week as well. And we had just stopped short of beginning to describe radio pulsars after introduction to some other aspects of pulsars. So we know now almost more than 2,000 pulsars, which are believed to be about possibly 10% of, or more than 10% of what we believe we can detect, which are probably 1/5 of 100,000 pulsars in our galaxy. Okay. So we know that we don't see all of them because they may not be pulsing, their beams may not be sweeping past us. So that factor is typically about 0.2. So we see about 20,000, we are expected to see about 20,000 pulsars, out of which we have detected more than 10%. And the rest of them are actually waiting to be discovered by people like you who would be searching for them in future. Interesting aspect about them is how they are distributed in our galaxy. They are largely born in the plane of the galaxy where the progenitors are. And then they, because of the kick that we discussed at the time of their birth, they are likely to migrate to different places well away from their birthplace, and they might be found even at larger heights away from the galactic plane. Typically they live, the radio pulsars live about a few million years to about a few tens of million years. Some of them 100 million years, and some of them comparable to the time, comparable to the Hubble time. And those are the ones which have got their second life through the spin up with the help of a companion, which is a low mass companion. They are spun up in the low mass X-ray binaries, and they can live forever. And so they can really be found at much larger distances from their birthplace. All right, coming back to the radio pulsar signatures, how do we detect them? We of course have to correct for all the propagation effects like dispersion before we can see their native signature, and all that is done. And of course, the pulsar signals are weak generally. So it's only after averaging many pulses we might be able to detect them. It is also on averaging large number of pulses that we see a signature which is characteristics of the given pulsar, which is its average profile. And so the typical picture we would see is what is depicted here schematically. We would see essentially pulse repeating at the interval of the period, the spin period of the pulsar. And we might see something in between which is called an interpulse. This is we see the emission. Seeing the bottom line in my, I hope you're able to see that. All right, okay. All right, so if you see the emission from the other pole, we will see the interpulse, and this will require certain viewing geometry, in the sense, certain angle that we make with respect to the rotation axis, and the inclination of the magnetic axis has to be within certain range, close to the orthogonality with respect to the rotation axis. But there are many examples of that, and you can we manage to see sometimes interpulse is as strong as the main pulse, to the extent that it might confuse you whether the period is really half of what the true period is. All right. The average profiles that you get after putting together thousands of pulses in a sequence are really something that we can associate as one-to-one with individual pulsars. They are like their signatures, and they don't change over time. Individual pulses might look different, but on averaging, the stable picture that you get is stable over decades, many decades, as we have been able to confirm now after their discovery more than 50 years ago. They also have well-defined polarization characteristics, which is shown here. The position angle is shown at the top as a line, which, you know, the PA in degrees is shown here. Also shown together with this continuous line is a dashed line and a dotted line. The dashed line indicates the polarized intensity profile, and the dotted line indicates the amount of circular polarization. So these sort of are the details, polarization details, but otherwise you will have a very stable profile after averaging many thousands of pulses. And there are people who would, just by looking at the profile, they will say, aha, this is this pulsar. And they have been characterized or classified in different ways, depending on the number of components one sees, and so on and so forth. And it's a pursuit in itself, which is pretty detailed. People believe these are manifestations of nested cone structure of emission, cones inside cones. And so depending on how we sample the cone, we will see multiple components associated with the multiple rings of emission that are centered around the magnetic axis of the star. So we have already seen the typical S-shaped polarization position angle sweep has a lot of information. Its slope becomes maximum at the center point of symmetry, antisymmetry, and that's also the point of inflection. And that is where you see the slope depends simply on some ratio of the trigonometric function of the angles, the important angles, this alpha being the angle between the magnetic axis and the rotation axis, and the beta is the angle between the magnetic axis and the line of sight to the observer. And then, of course, combination of alpha and beta is zeta, which is the angle between the rotation axis and the observer. All right. So people actually use this profitably to model and infer these quantities, which form basis for lots of investigations, lots of interesting investigations. associated with the way magnetic field is oriented with respect to the rotation axis and with respect to us, so that we can interpret the emission that we see in terms of what might be happening on the star. All right. Now, we talked about the average profile, which we said is very stable. This is in stark contrast with what we see on individual pulse basis. This is a sort of raw time sequence of intensity as a function of time when we are observing a pulsar. You can see, apart from the noise, which is pretty large here and naturally random, we also see wild variations in the pulse intensity from pulse to pulse. We also see additional things coming in and going up, appearing and disappearing. And so when we stack these pulses by cutting pieces equal to the period and laying them on top of each other, we can get what is called a stack of pulses to see how things are varying from one pulse period to another pulse period. That means as a function of time. And then we can zoom in into the what is called the pulse window, which is rather small in most cases. It's about 5 or 10% of the period. And so that zoomed view is what is shown here typically for one of the pulsars. This is one of the nearby pulsars. You can appreciate very quickly that while this is the average profile of this pulsar, remember there is long interval of no emission around this pulse before this pulse reappears. So we are looking at only 5–10% of the entire interval, which of course repeats for every spin cycle. But when we do that, we will see that while this is the average profile, the individual pulses hardly look like the average profile. They have very, very different looking emission distribution within this window. It is only after averaging all this that we will get the stable profile. People have interpreted this as being emission entities, which might be telling us pretty important things about the emission process itself. But they occur with certain probability in different places, and it is average profile which is made of different components. The components really indicate the distribution function of appearance of intense emission. So that's the essential interpretation. So this is like the envelope describing the emission, and within that you will find the emission might occur anywhere. It would occur more often in these places where the peaks are, and so on and so forth. Also, it might be a little more intense, but all that is a combined effect that we see in the average profile. At very high resolution, you might see details going down to a nanosecond, which is very spiky emission, and so it is like sputtering occurring quite randomly, but systematically enough to build up intensity in certain preferred locations, which are delineated by this average profile. All right. While we talk of radio pulsars, the natural question is, are they visible only in radio? No, some of them are detected at other wavelengths too. And you might have already heard about it in greater detail in Sushant's talks. The young ones particularly are detectable at high energies, optical X-rays and gamma rays. And in gamma rays particularly, after the Fermi survey and search, one has actually found large number of pulsars which radiate in gamma ray, but may or not radiate in radio. And that's something that initially seemed to puzzle people, but if you look at the emission processes or the essential happenings in the magnetosphere of the pulsar, one wonders why one is surprised to see them in gamma rays. They should naturally be visible in gamma rays. They may or may not produce efficiently radio radiation, or may not be visible because the cycle line may not sweep past us. But there are more natural sources in gamma rays, as we will see. All right. Before I move away from this slide, let me point out that the emission profiles also might differ significantly. For example, the classic example of the Vela pulsar, where the radio emission is seen as a single pulse within the so-called main pulse window, and nothing in between, whereas the gamma ray profile shows a very clear interpulse. Now, it's almost suggesting that we should have ideally seen this emission from the second pole, which is certainly seen at gamma rays, but it's missing in the radio. So one needs to understand why. This will require a very specific geometry, inclinations of the magnetic axis and rotation axis, and with respect to our direction as well. I will come back to this aspect a little later in the context of pulsar wind nebulae. All right. Now, just observationally, one has seen that when we observe this pulsar at different wavelengths or different radio frequencies, we see pretty significant evolution of the pulse profile, as can be seen here. The first thing you will immediately notice is, apart from the fact that the relative intensities of these two peaks appears to be different, certainly the separation between the component is seen very systematically increasing as we go to lower and lower frequencies. And this is understood very simply as the one-to-one correspondence between, or at least more readily understandable correspondence between where the emission at a given frequency would be strongest, and that one can see, one can work out from simple dependencies on the magnetic field strengths and the curvature of the field lines, that the high frequency emission would come from very close to the star, and low frequency radiation will come from farther out in this cone of emission. And given the dipole geometry, one can work out how the angle made by the tangents of this last open field line, or the lines delineating the cone, how that changes as a function of height. You can see very clearly that the tangents are much more closely spaced, separated when we are very close to the star, and they make the wider angle as we go away. And this is manifested here to the extent that one can even begin to check whether the geometry is really dipolar, or how good a dipole geometry describes this evolution. And the answer is that particularly well away from the stellar surface, it's almost purely dipolar geometry for the magnetic field. All right. So this is something that people have investigated even from the archival data in great depth, and any anomalies seen in different in a given pulsar would lead to questions about the essential geometry of the or the dominant multipolar structure, if it exists, particularly the deviations seen at very high frequencies, which are not unusual. All right. Now, one of the things that was realized soon after the discovery of pulsars was that if you, once it was clear that the emission is coming from a very compact source, you can ask what kind of brightness this object needs to have if it were to be a black body to emit so much radiation at this frequency based on what we receive and scaling by the distance from us. And this calculation can be done very quickly, and you will find that the apparent equivalent temperature of the imaginary black body, which will produce such a radiation, would be very high, to the order of 10 to the 30 Kelvin or something like that. And this is simply not producible by any known process of incoherent emission from no matter how big an object is. Because processes like some regulatory processes within the region of emission and the surrounding will take over and limit the apparent brightness to about 10 to the 12 Kelvin. So it was clear that like in masers and lasers, we must have a coherent emission process involved, which can be stated as simply as a large number of charges radiating in phase, where the radiation fields superposition of that gives you an n times increase in the field strength, radiation field strength, and that gives you n square gain in the intensity as compared to n times increase that you would get in the incoherent case, where the intensities add rather than the field. So by invoking large number of particles radiating together, people have been understanding this, and one can be assured that without such a coherence in the emission, none of the radio pulsars would be visible at our distances, given their small sizes and the kind of amount of radiation that they can ever produce if it were not to be coherent. So of course, this brings in a requirement necessarily that we need a situation of large n, where we need large charge densities in the region of emission. And the question is how to generate these. And this was pretty, this was an aspect which was addressed very early on by Goldreich and Julian in their classic paper of 1969, soon after the discovery of pulsars, where they there is a super dynamo at work, which is simply a result of rotating magnetic field. And there will be gaps where large amount of potential difference would exist of the order of 10 to the 12 volts or something like that, which will also imply large electric fields because this potential difference will be there over a reasonably small scale of typically about 50 meters or so. And so you can imagine a wonderful accelerator being created close to this, what is called polar cap, which is the region right above the stellar surface and of the extent which is within the cone of the last open field lines. And the last open field lines are basically defined as the ones that manage to, other than the ones that manage to close by the time the co-rotation speed becomes speed of light, which is the boundary identified and marked as what is called a light cylinder. So lines that manage to close within this will be treated as closed field lines, and there is no real action there. It is along the open field lines which appear open, and people need not get perturbed about monopole aspect here because they will close through the interstellar medium well away from the region that can co-rotate. Of course, the structure of the field will be no longer dipolar beyond this point, and even within this boundary closer to the light cylinder, there will be distortions because these field lines are not just in vacuum. They are loaded with charged particles, and that will show inertial effects which will drag the field lines behind. All right, so they worked out this electrodynamics of this object with where there is strong dipolar field which is in rotation, and they worked out what kind of electric fields and potential differences will exist, and also calculated the charge densities that this will produce. So they basically stated that these are the magnetosphere is largely filled with charges, and the charges will arrange themselves to cancel the field in most of the region except very close to the stellar surface, and also people believe along the last open field lines. So these are the polar gap and outer gap regimes where there will be a potential difference. So there will be electric field which is parallel to the magnetic field in this region where my pointer is, and elsewhere the electric field will be zero because of the rearrangement of the charges. And so they asked what is the charge density required to produce this cancellation, and they came up with this estimate which we'll come back to. So essentially this is the mechanism for producing large number of charged particles. How does it actually happen? You have this, now we are zooming on to closer to the surface. So this is the stellar surface, and this is that about typically 50-meter gap that I'm referring to, where the electric field exists. Outside the electric field is zero. So this is like a capacitor with potential difference, and you throw in any charged particle there, it's going to get accelerated to TeV energies, given that the potential difference is of the order of 10 to the 12 volts. And as it interacts with the magnetic field, you will find it will produce electron-positron pairs. These pairs produced within this range where the electric field is non-zero will of course be influenced by the presence of the electric field. So certain charges will flow downward to the stellar surface, and the other opposite charges will flow out. It will happen in a cascade fashion here. The electron-positron pairs themselves are energetic enough to produce further pairs on interaction with in the presence of magnetic field. And this cascade continues while charges really leave this region. So because of large acceleration and the fact that anything here will quickly be taken out of this region because of acceleration and high speeds that they will attain, this essentially can be treated as a vacuum. This is like the traffic on the road where vehicles are moving fast, you will find the density of the vehicles small. So this is called the vacuum gap, and this is where the large number of charges are produced. Of course, this process continues outside as well, where the charged particles which escaped and were still energetic will continue to produce electron-positron pairs, except the pairs now are not under the influence of electric fields, so they will move in the same direction of the other particles. So essentially, we are producing gamma rays, which are radiated by this charged particle moving in the magnetic field, and then the gamma rays produce the pairs, and so on and so forth. So there is a continuous production of gamma rays as well as pairs. So as I said, gamma ray production is more natural to this process of radio pulsars because they are needed to seed this entire activity in the first place. All right. So the cascade is so intense that we really have an avalanche once the seed is available to produce the cascade. And so we have a large number of particles produced, and the charge densities were estimated by in the work of Goldreich engineer. All right. So essentially, the picture is we have a powerful dynamo. We have a large potential gap produced where the electric field is intense. And then we have acceleration of charged particles, radiation, production of gamma rays, which when they interact with the magnetic field produce pairs, and this pair cascade continues. And so we have a relativistic particle flow along the cone and the field lines, and which will see acceleration as they move along the curved field lines. And it is the curvature of the field lines and the relativistic particles flowing outward that produces the radiation. And so it's tied up with the curvature and, of course, the Lorentz factors of the particles which are radiating. But it should be remembered that the radio emission that we see is a tiny, tiny fraction of the rotational energy loss rate. The essential radiation that I mentioned earlier is really at the low frequency, and the frequency of the spin of the star. That radiation, as I said, doesn't get very far, but we get to know about presence of those objects, not because of the major energy loss that they have. It's because of some tiny energy loss that they also incur because of the process that I just described. So thank God they produce some radio radiation that we can see. We would not have seen them through the dipole radiation that they produce. All right. Although we said all these things as if we understand it in great detail, the key details of the mechanism of radio emission, particularly the coherent amplification, are yet unclear. There are any number of models which invoke maser-like mechanism. Some invoke some plasma processes, the negative optical depth, and some plasma oscillations, and so on and so forth. So there are a range of models. The simplest one is what I've described, where a large number of particles radiate coherently. It's a good working picture to proceed with. All right. So the essential picture is this, that we have these last open field lines defining the radiation cone, and all the action is seeded from the bottom here, and which manifests itself through radiation of large number of charged particles moving along the field lines, curved field lines, which radiate locally tangentially. And so that's what defines this radio phone. All right. How have we? How do these things square with what we actually observe? And in fact, it's the other way, that it's through observations of many of these objects in radio and their details, we have got rich clues about the details that I said we are otherwise missing. So these details are visible at individual pulse level, although some broad scale information is available in the average profiles. But when we look at this from pulse to pulse, we see a lot of fluctuation, as I described. We see sometimes very systematic variation in the intensity, where we will see drifting subpulses. That means small entities of emission are seen to shift in the pulse phase. Location of the emission changes systematically, and then it restores back, and so on. Sometimes the pulsar disappears completely, where it's called nulling, and Sushan has talked about it. Many of you might be doing some interesting projects already with her on this. While I said pulsars have this very distinguishing signature of their own, which will help you to identify them with their names. They sometimes keep more than one signature, one in their certain mode, and another one, like some people have for their personal dealings, one signature and one official, and so on. And they so pulsars seem to change from one to the other without any warning. It's not seen to be any periodic, but they have more than one mode, and they can go into that mode for thousands of rotational cycles and then return to this sorry for that disturbance. Just a minute. I will have to stop my video and I'm so sorry for this. This is something that is.
No problem, no problem. We enjoyed the music.
This is a new place. Everything is pretty strange here. All right. So I really apologize. I was hoping there won't be any disturbance today, and it exactly happened pretty much the same way as it happened last time. All right. So we were talking about the pulse profile changes. It can have more than one signature, but they are again pretty stable or individually pretty stable. One also sees that similar thing is true for polarization position angle, which follows this nice S-shaped curve, which is characteristic of the given pulsar and its viewing geometry. But there are often cases where one sees a 90-degree jump within the at a certain phase of the pulse, where instead of the angle being some phi, it's phi plus 90. And this happens again without much warning. People have been using this as an additional clue to begin to understand what really decides this polarization, and whether it gives any idea about the. So in general, people believe that there is superposition of two orthogonal modes always, and one of them is dominant, in which case you will see position angle of one kind. But both of them follow the S-shaped curve, as you will see. Yeah, so just one more. All right, so this time there was a knock on the door rather than the music. Sorry for that. So the other important clues, set of important clues come from very short scale structure in time, which is of the order of few microseconds, or sometimes even finer than that, which is spiky. It's like spark discharges, and this is what one believes is the essential characteristic of the emission that comes from the pulsars. And it is the envelope of those that microstructure that we really see as the profiles that we talk about. At the basic level, it's like a short noise, people believe. And so that is relatable to the sizes and of the entities that might be radiating. One also gets sometimes huge intensity pulses, which are 1,000 or 10,000 or million times stronger than the normal pulse intensity. And these are called giant pulses. Crab pulsar is prolific in producing such giant pulses, and they have been studied in great depth. One clearly sees that more intense the pulse is, more rare it is, and that's what we would have expected. But these can exceed by large factors the average intensity. So there's a lot of pioneering work done in all these aspects by a range of people, and this continues to occupy the traditional pulsar astronomers' mind, and more clues keep coming, and for every thing you begin to think that you understand it, there is a counter example that one of the pulsar shows, and then you go back to the board and try to understand how it fits in with the broader picture that other pulsars seem to indicate. All right, so this is continuing, and a lot of this work can be done using archival data, as I have indicated in this color code. All right, I should look at the time. How am I doing with the time?
Fine, you have 45 minutes more.
Okay, all right.
Yeah.
All right, so I will pace it.
Or maybe half an hour, then we can give 15 for discussions,
okay.
As you prefer.
Okay, let's see how it goes, given that we had these interruptions. Hopefully, there won't be any further.
But you can go till beyond also.
Okay.
Yeah, there's no issue. They're all.
Yeah, it will depend.
The interested ones.
Depend on the patience of the listeners as well. So, anybody, please feel free to ask us to, conclude for this session and wait for the next session to say the other things. But because I'm not seeing the time in front of me, I have a clock here. All right, so let's come to one of the most fascinating observations that, at least to me, something that clarified one of the most nagging aspects, or or discomforting aspect that we had for many decades in pulsars, pulsar emission. We knew that the pulsar is slowing down, given its, and people tied it up with the loss of rotational energy due to the magnetic dipole radiation, and even use it profitably to estimate the magnetic field, comparing the radiation power and saying that it comes at the expense of rotational energy. All that was fine. We also knew that there is a large number of particles which are responsible for producing the radio radiation, and given by the Goldreich-Julian density, both the number density as well as the charge, the current density. And given all this, and that they need to be relativistic, we knew that there is a large number of particles flowing out, and of course they should carry some energy, and we had no idea of where that, how that manifests, or how to include it in the first place, whether it is important or comparable to the other modes of energy loss. And this was clarified by this very beautiful observation by Kramer et al. Of what they call a part-time pulsar, which radiated for a few weeks. And this is something that I mentioned last time briefly in response to one of the questions. And so when they looked at the rotational rate, they found that the rotational rate should evolve, as we know, but it evolved differently during the active times, and as an overall decrease, where they saw faster loss of energy during when it's active, during the periods when it's active. And this immediately clarified this aspect of this additional energy loss that is occurring due to the particle flow. And so this is additional braking due to the charge flow. And remarkably, this is a triumph of the theoretical robustness in the theory that Goldreich and Julian put forward, that when you see what this extra energy loss is, which is on top of what is described by this overall rate, you will find that it corresponds to the charge density and current density that Goldreich-Julian predicted to the decimal place. Okay, so this is very reassuring, and now we know that not all the energy is lost due to the dipole radiation. Almost as much is lost due to the particle flow and the energy carried away from them. And so people might actually have to go back to their estimates of the magnetic field and account for this, and don't be surprised if their estimates will now weaken the field by a factor of by typically √2, assuming they're sort of equal contributors to the breaking, the charge flow as well as the dipole radiation. All right. So this was very clarifying and satisfying, and now we have a handle on. We can measure in cases where we can see clear nulls. Those are the periods where we can assume that there are no other energy losses than the dipole radiation, and we can also estimate the energy carried away by the outflow of particles from these two cones. We talked about microstructure and as something that will give us clues about the details of the emission. People have indeed seen structure down to nanosecond, And so if you really use light travel time argument, you will see a nanosecond structure cannot be produced or cannot be retained without smearing unless the radiation came from a very tiny region. And you can estimate that it will come out to be a beach ball size, which is what Hankin's observation from Arecibo telescope illustrated, where, of course, coherent radiation is produced by this small region. You can imagine to produce a radiation of the intensity that we see, you will have to have large charge density there, given that size is even smaller than the typical polar cap size. Of course, when you have, you can see micropulses distribution, which might follow a pattern like this in some pulsars, and which is reminiscent of diffraction pattern. And the way people have tried to understand it is like in early work of Stark, who had proposed that there are sheets of charged particles flowing outward, and we will get radiation from them, coherent radiation. And so this coherent radiation will, we will, of course, from this coherence, if you sit on this sheet, you will see, because of the flaring of the charge, flaring of the field lines, the charges are moving outward from the center of the sheet. This is in the co-moving, for the co-moving observer with the sheet. But because of the flaring of the charge, flaring of the field lines, you will still see charges migrating outward. And this is like a center-fed antenna. And with this current field, you can estimate what the radiation field will be. And it turns out to be what is shown here. And we might be cutting this pattern at some distance from the center, and we will see this pattern. Indeed, something similar has been seen in the distribution of the spiky emission that one sees. Individually, it might be pretty narrow, but it occupies these locations preferentially, as if there is an envelope dictating what the intensity should be. And so this is, we believe it's a diffraction pattern associated with the coherent radiator. And more can be learned from this in terms of what we will see when the pulsar is rotating at different speeds, and what is the distance that it traverses before the radiation escapes the magnetosphere and we see it. So whether we will see it as a spike or we will see this as a continuous pattern will depend on the relative timescales. All right. Coming back to this phenomena of drifting subpulses that I mentioned, it's illustrated in this diagram here on the right, where on one pulse we will see the emission, let's say, at these two locations, which as subpulses, smaller entities of emission. And these might appear with a shift in the next pulse, and with progressive shift in the second one and the third one, and so on and so forth. And this pattern might restore itself after so many set of pulses, not necessarily integral number of pulses. And so this will appear like individual subpulses are marching systematically and then coming back to their original location. This was this motivated additional aspects to be included in the famous Ruderman and Sutherland model, which is one of the most comprehensive models put forward early enough in the game in 1975, where they invoke this polar gap, sparks, and drifting subpulses. And so in their picture, the emission is confined to spots which might be arranged along a ring or multiple rings around the magnetic axis. where discharge takes place, which is what we said, a charged particle in this acceleration zone will produce electron-positron pairs based on the electric field sign and the sign of the charge. The charges will move in appropriate directions. And this is nothing but a discharge in a capacitor, okay? The cascade that it produces and the current that is seen at a given location where the potential gap will actually reduce momentarily and will restore itself after the current dies off. And so that will define locations of these and these locations themselves drift under what they invoked as E cross B drift. They invoked an electric field which is perpendicular to the B, a small component of electric field, in addition to the one that is parallel to the electric field, magnetic field within this gap. And so that will cause a slow drift of these discharge locations about the magnetic axis. And they even estimated what that would be. They had even a specific number, which of course is not seen to hold very well. And this has led to several other ways of estimating it and so on and so forth. So this is something that can be still also studied or taken from the archival data, and there is still a lot to be understood in terms of how it depends on the magnetic field and the period. Or does it depend on anything else? So the picture is simple, that you have these entities along a ring and they are undergoing some drift. So this is this azimuthal rotation of this system of spots. And if our line of sight is sampling along any chord, we will see this emission appearing there in one pulse. But in the next pulse, we come around, the same spot has drifted to another location. So that's what will make the pulse appear at a different location, the subpulse appear at a different location. And then, of course, the next charge entity will come, or next emission entity will come in the view later, and so on. And that's how this repetition as well as marching is understood. Okay, so we had asked this question that if this is indeed the case, and if we can determine the rotation speed somehow, which we were able to in some of the cases, we are really seeing the details of this pattern. Although we cannot see the pattern as a whole at one time, we are shown different parts of the pattern at different times, and if we can put all of them together, we should be able to build up a picture of the entire pattern, and we in fact can do that. And this is how the pattern looks like. And this certainly allows you to now begin to monitor the weather in the magnetosphere, what we call pulsar weather. And the details, of course, you see are at the level of pico arc second resolution, which is so natural to pulsars given their the probing axis being the time and you know, the region being small, the details get translated into small physical distances, and those physical distances at this distance of the pulsar will correspond to very tiny angular sector. So this is like seeing a bacterium scale detail on the Jupiter distance. So of course there are dramatic things happen seen in this particular sequence at the end of towards the end of this sequence after about 800 pulses. And that's a mode change that I was talking about. It changes its signature suddenly. And that can be, you know, related to the change in the pattern and all that. All right. Now this is a ring that you saw, but this is because we intercept the cone at a distance so we have no information about the inside within the radius at which we, the closest we get to the magnetic pole. But there are cases where we get pretty close to the magnetic pole, as close as here, in which case we'll get cuts instead of a small chord, almost diametric cuts. And then by seeing these cuts, when the pattern rotates, we can reconstruct the pattern as a whole, as shown here. And we can really get the details of the emission in much more detail and completeness as shown here. So I'll not go into the details of what we can infer from this, but you can already see two rings of emission. The same pattern is seen in the inner part, and in fact that itself was an important finding, that the same pattern is seen in the inner part, and it's highly correlated with the outer in their behavior. And there is a small shift in this pattern, which made people to infer that it's essentially the same seed activity at the bottom, the discharge activity that we described, which produces the secondary particles and the large cascade of electron positron bunches which radiate, and the same pattern leads to emission at, if it leads to emission at two different heights, we will see different cone sizes associated with this. So this is at lower height and this is at higher height. And then because the same charged particles are flowing, the same morphological pattern is at work, we should see high degree of correlation between them. And if there is any distortion in the field lines, like a twist, then we should see that in the way the pattern is azimuthally shifted with respect to this. Indeed, we can infer all these details even from archival data. All right. Now, to really check whether this is true, in general, even in the case where you don't see multiple cones, one needs to probe this with by making observations at different heights, and that can be easily done by observing the pulsar emission at multiple frequencies simultaneously to check if there is any seed activity common to emission that is seen at all the heights. Although the similar pattern are seen at different frequencies, the really evolution of an individual entity as a function of distance or time after it's emitted at high frequency at the bottom, and how that relates to the intensity changes at greater heights requires this simultaneous observation. Of course, instrument to do that didn't exist. So one built such an instrument, and we had actually a lot of fun where we put a receiver on the green band telescope, which would work at 10 different frequencies simultaneously and produce, help us produce a tomographic view of the magnetosphere, which is shown here for one of the pulsars, which is a famous drifter. You can see that these entities now at different frequencies are now mapped, and we can actually begin to see the evolution in greater detail as a function of height. All right. We have said pulsars. Now I'm going to tie up this picture of both the particle flow, which is so clearly implicit in the way pulsars produce their radiation and radio. Without all that action of dynamo pair production and large number of charged particles radiating coherently and moving at relativistic speeds, we wouldn't see the radio radiation. We will now see what how this ties up with the so-called pulsar wind nebulae, which are produced from produced due to the wind, this particle wind that comes from the pulsar so naturally. But we know that the pulsars are moving as well. So they move away from their birthplace and can be found at a significant distance from the center where they might be born. So while this is a nice supernova remnant, shell type remnant, the pulsar is seen at some location here and appears to come from a direction like this based on its present direction, of course. But along with it, wherever it is, it's also producing its own nebula, and because moving at a fast speed, you will see that the nebula is sort of even left behind. So there's a lot of interesting situations that are seen, both in terms of what the pulsar wind does when it interacts with the surrounding, and the fact that pulsar itself is in motion will add to the additional details and structure that we see in this nebula. So these are some things that you can, one can do, still not completely done. People might have missed lots of these associations where there might be a pulsar and there might, so there might be lots of supernova remnants known with no pulsar association. But although the pulsar may not be pointing towards you, its presence in terms of the wind nebula that it produces might be clearly evident. And so a lot of fun can be had to identify such objects which may not be visible readily as supernova pulsar association in the traditional way of radio pulsar detection, and then finding it associated with us, nearby supernova remnant. Okay. One example that I'm going to talk of in terms of the way this wind interacts with the surrounding is the classic case of the Vela pulsar, which shows a beautiful X-ray nebula surrounding it, which was accidentally imaged when one wanted to actually see if the glitch produces any X-ray radiation enhancement. In the process of making that observation with the Chandra telescope, this beautiful image was made by Helfand et al. And where lots of details are seen very clearly. There are well-defined pair of arcs here. There is bisecting these is a feature, a jet-like feature or something which gives you a symmetry axis of sort, which also happens to point roughly in the direction of the motion of the star, which is indicated by this green arrow. So this is a picture in X-ray. The similar morphology is seen on a much bigger scale, of course, in the radio. So this nebula that you see here is shown here in this small region, and this is the radio nebula, which is almost 10 times bigger in area than the X-ray nebula. So people have been having this picture of that there is an equatorial wind from the pulsar, which is dissipated to become a source of synchrotron radiation, producing this compact nebular structure. And this equatorial wind is indented in between, where you have magnetic field going to zero, changing the polarity, because of which the emission is weak. Otherwise, there would have been a band of emission like this. And this is how and there is a Doppler boosting because of, stuff moving, the flow moving towards you. One can estimate, given this distance to this pulsar and the angular size of UC of the nebula, that we are looking at this radiation on the scale of about 1 light month or something like that, while the object itself might be 1,000 light years away. Okay, but we have a very different interpretation of this, and let me see if I can convince you of this. The X-ray arcs we feel are traces of the radiation beam, which are the particle beams from the two poles. These flows, collimated flows of charged particles, which are inevitable, are almost essential to produce the radio radiation. We never asked what do they do when they interact with the surrounding medium. When they encounter the walls of the so-called central cavity that I described, pulsar produce because of their dipole radiation, which cannot escape due to the surrounding medium. We can ask what this charge flow, particle flow will do when it hits this wall. Of course, it will dissipate its energy and produce a glow of light that we see. So this is just extending the rotating vector model. In fact, this is the rotating vector model where we have hosts of two-ended hosts of charged particles throwing the paint on the wall, which is wall of the cavity that the pulsar has produced. And what will it trace? It will trace two circles in general for a cavity which has got some cylindrical symmetry about the rotation axis. And when it's viewed by some observer, it will look like ellipses. The ellipses will have certain regions where the emission coming towards you is boosted, where the particle flow is towards you. And so it's like brightening two arcs associated with the two circles, which appear like ellipses, where you see bright emission. And this is simply tied up with the simple geometric picture of the magnetic dipole rotating. We can actually check this for its association with this picture. Indeed, you can work out the viewing geometry of the star and actually see that these are indeed the true traces of the two poles. So where the pencil beam of charged particles will produce this. The jet-like feature here, which needs more discussion, I will not go into the details of it. I will give you the essential features of it. People believe the prevailing wisdom is that there is, much like in micro quasars, there is flow of charge, physical flow of charged particles along the rotation axis. Now, we would like to remind everyone, as we have done multiple times in literature, that this pulsar in which we are discussing this aspect, like the Vela and the Crab pulsar, where similar things are seen, are not accreting objects. They are isolated objects. And a jet along a rotation axis is not only unlikely, but unphysical. There is no accretion occurring. There is nothing asking for action along the rotation axis. If at all there is any action, it's only along the magnetic axis, because that's where we have seen the dynamo at work and everything else at work, and the particle flow is also along the magnetic axis. And so if at all there is any action, it being along the magnetic axis, it might appear to us that it's happening along the rotation axis if we see this emission only when the two axes projections are aligned. So we might mistake something happening along the rotation axis because it's actually happening along the magnetic axis. But we see that only when they are aligned. We might mistake it for action along the rotation axis. And so this picture is where we have a relativistic flow of charged particles leaving the magnetic poles, proceeding ballistically towards the cavity wall. And we can ask what deviations that they are likely to suffer. And you will find that the only field that they see is the toroidal field that comes about because of rotated poloidal field beyond its beyond the co-rotation regime, where it will get wound up and will have a toroidal field. So we have a situation where we have the particle flow outward, which is perpendicular to the rotation axis and also perpendicular to the magnetic field orientation because it's wound around azimuthally. So we have a radial flow, right, which is largely perpendicular to the rotation axis. And so this will, you can immediately see that there is a magnetic field perpendicular to it. And you will see that the particles which are flowing along this pencil beam will see magnetic field like this, and they will get deflected due to Lorentz force in the direction away from this, but in the latitudinal direction, only along the latitudinal direction. So with this pencil beam, you will also develop a fan beam of charged particles. And when they radiate well away from this collimated direction, you will find light coming also from them. Now the question is, if you see this light only when this entire system of pencil beam and fan beam is pointing towards you, much like the way you see the pulse when this cone is pointing towards you, you will see this fan beam extent of
We can't hear you, Dish. Hello. Yeah, just be online. We'll be back soon. Still be back. Huh? There's some power failure with a speaker. So Professor Desh will be back soon. He's rebooting. So just stay online. Okay? And or ask, type in questions in the meantime. If there are any questions,
Hello,
yeah. So,
am I seen back? Okay.
yeah, you are back. I'll just share, make you co-host. So you'll have to share again.
Okay.
Yeah, we can see the screen.
Okay. So I'm. Okay. All right. Appears like working in olden times with very poor technology. Um,
Need not to worry, it's fine. It happens all the time.
Set up things is enough. I thought only the power failure can come in the way, and it did, as Murphy's law would have it. Anyway, so we were talking about this radiation, the particle flow that will occur along the pencil beam naturally, but it can also spread into a fan beam, and then radiation from the charged particles moving outward can also come from not just a spot, but can also come from a wider angle. So the pencil beam will produce the arcs that we see when it encounters the wall, and on the way and at the wall, you will see radiation from the fan beam. The fan beam radiation will be seen as a flash when it points towards us, which is when it appears as if the radiation is coming along the rotation axis. And when it hits the wall, this particle flow will produce a glow, exactly as shown here. The flash of light is seen when it's pointing towards us. Otherwise, on the wall, it's producing this glow along a band, which is cylindrically symmetric, but seen at an angle, it will look like this kidney shape for the viewing geometry that we have. Now, this combined with the picture of the arcs that we get from the pencil beam, we can reproduce almost the morphology that we see. This is the observed picture, and this is the simulated picture from just this geometric description. Okay, all that we are saying is we have radiation coming from the particle flow when it interacts with the surrounding. Okay, either on its way to the wall or at the wall. All right. So that's that picture. I will show you examples if we have time, how this will appear differently to different observers. But let me proceed to mention the excitement that came soon after when people observed this nebula multiple times during the subsequent years. And then they saw that things were appearing to change. And they put together that in a sequence of pictures played in this fashion, where the zooming onto this jet-like structure, one saw it dangling. So these were pictures only of about 4 epochs, but they already saw the variability in this jet-like feature. What they did not notice is also that if you look at this nebula as a whole, it's also undergoing a lot of change from epoch to epoch. And if you pay attention to some of these appear saturated in intensity, but if you look at it carefully, so it was very clear that there is something happening over a large scale of the nebula itself. Now, such correlated variations across the nebula is impossible to coordinate unless there is a central message from the pulsar, because otherwise there's not enough time for one part of the nebula to communicate with the other part to do something similar, which means that there is something happening at the pulsar which is responsible for this variability. And a natural explanation popped out, which is also tied up with suspected behavior of this pulsar based on the variability that one had seen in radio, where we had interpreted close to a year periodicity as evidence for pre-precision, not to be confused with a yearly variation. And we see that the present view in X-ray provides excellent support for that conclusion. And that is actually the interpretation one has of this variation, which can be checked by simulating this nebula with precision put in, and this is how it will appear. I don't see, let's see, I think this No. Okay, the simulation is not seen, but I can show you what was really observed subsequently using the Chandra telescope. And these are many pictures put together now. And you can see this jet doing an outward conical spiral behavior, which is a manifestation of precession. And so it's been confirmed now that Vela pulsar is indeed precessing. One can ask if this picture, geometric picture, is relevant to, defining the morphology of the nebulae that it produces around it in other cases as well. Indeed, we take the other famous object called the Crab Nebula, which is the beautiful nebula produced around the Crab pulsar, which is pretty young pulsar. And you can see that this is what one sees in X-rays. Here it's a composite of, the previous picture was a composite of optical and X-ray picture. But this is the X-ray picture alone, which shows great amount of details, including a bent jet and so on. And all that can be reproduced by this simple geometric picture, which as we refine, we take the simple viewing geometry first, and this is the picture it will produce. Then we take other details of breadth around it, of the particle flow. And then we put the precision, which was seen in the gamma ray intensity for 14 years period, and you can begin to produce the bend that you see. And then you put additional, if you see monoenergetic flow, then this is the picture you would get. You give a spread of energies, and then you produce this picture, which is pretty much like reproduction of this. Of course, there are other details which differ, and in fact, they can be used to understand the details with the flow and other things. So anyway, it's, so while we invoked this particle flow as an essential ingredient for producing radio radiation from pulsars, we never asked what this flow will do when it interacts with the surrounding. And we have actually seen evidence of it and manifestation of it in a beautiful way through these examples that I've shown. So there are many examples of like this to be seen and studied from the archival data, which might be freely available. Evidence for pre-precision also can come from pictures taken at multiple epochs. One of the things that I would like to point out is that remember my mentioning the second pole radiation not being seen in radio, but manifestation of it is seen very clearly in the in this nebula as an arc associated with the second pole. So you can get the viewing geometry more refined with such pictures that will come not from the pulse radiation from the pulsar directly in radio, but from the structure in the nebula that it produces around it. So there are lots of stuff to be learned from even the pictures taken in X-rays and so on of nebulae around. Even to identify them that they are nebulae. Sometimes you may not see the pulsar. You may not be even aware that there is a radio pulsar there. But it's writing on the wall in terms of the nebular emission would be visible. And so this is what I mean by, you can actually have, through X-ray observations or even radio observations, detection of nebulae where the pulsar itself may not have been visible. So Of course, the mysteries related to pulsars will continue to be heard. For the future generation, there are at least two holy grails that they would look forward to discovering. One is sub-millisecond pulsar, the other one is, of course, black hole pulsar binary, which will allow a very different regime of test of GR. And of course, people are hoping that they will detect gravitational waves with the pulsar timing array. People like me would be concentrating on understanding emission mechanism better, and so on and so forth. So I'll probably stop here and take questions. I'm already out of time. So thanks for listening.
Thanks a lot, Desh. Any questions, please ask.
Okay.
Please put your questions in the chat window or unmute yourself and speak.
I don't see any questions.
I have one, but not related to this. Sorry. I wanted to know that about Arecibo, right?
Oh yeah, it's creating news right now, right?
Yeah. So would you take it as that the science funding is, I mean, do you take it as, do they have a genuine reason to close it down, or is it just being a way of cutting funds and things like that?
No. I think right now there is there was a mishap about the structure of the rope structure that supports this hanging triangle, as they say, or the stuff that carries the receivers and focus. And after that was broken sometime few months back, there has been another cable breakage which has raised doubts or raised concerns about the safety of people who are trying to help this situation, including people going under the dish. Might have something falling from the top, and which is actually true. There are real safety concerns because that structure is so huge. It already created a big hole in the dish when the first cable
there
fell.
are the satellite images which show, right? The satellite images show.
So yes, I think it's less to do with the funding. What is not clear though, that I personally feel there is a way to, at the most, there are few cables broken. After all, there were no cables when the structure was getting built, right?
Yeah.
And things will require replacements and so on. If they really undertake overhaul of the support structure, they, might be able to revive the whole thing. Instead of abandoning now because of immediate safety concerns, they can, through helicopter, remove all the weight and reasons that might cause damage. But I think abandoning that entire dish. So I'm hoping that some bright thoughts might occur to people who are otherwise.
Yeah, because what they're doing is like the last resort, this thing, right? Just close it. I mean, that doesn't make sense. I mean, that's why I wanted to know.
And then these are ground-based facilities. They go and repair, space telescopes, HST and space station. And how much of a risk could it be to do something here? I'm sure they can fix it up.
Hello? I think we've lost you again. Oh, he's there. Hello.
Hello.
Okay. Okay, then we'll just wind up
Yeah.
because.
Okay, so let's stop the session for today.
And keep your questions for next Saturday session.
Yeah.
And next Sunday is when we'll be finally finishing these series of lectures. And then all of you all would be busy with your projects, etc. Right? So you can give us your feedback on Sunday also, because Sunday we'll wind up all these weekly sessions, Saturday, Sunday sessions. Right?
Anyway, we'll be meeting tomorrow at 10.
Oh, yeah, we're meeting tomorrow.
10. Okay, then.